Hi, I am Ifan and Patrick, and in this video, we're going to look into base 2 or binary system. When we talk of base 2 or binary system, we mean a number system with placeholder of 0 and 1. And basically, this number can be also called the digital system. And base 2 number system is often used in switch applications, which is the backbone of digital electronics. Now, a typical digital electronic systems often make use of on and off, often represented by 1 and 0.
And then if we are to count from 1 to 10 in digital or base 2 system, then 1 is going to be equal to 1. Then 2, since the highest value we can have in base 2 system is 1, 2 is going to be equal to 0, 1. And then 3 is going to be equal to 1 and 1. Because we are actually filling this value here. We've not passed the value 1. Then for 4, 4 is going to be equal to 1, 0, 0. And then 5 is going to be equal to 1, 0, 1. And then 6 is going to be equal to 1, 1, 0. Then 7 is going to be equal to 1, 1, 1. And for 8 is going to be equal to 1, 0, 0, 0. And then 9 is going to be equal to 1, 0, 0, 1. And then 10 is going to be equal to 1, 0, 1, 0. Now you might have observed that base 2 system requires more bits of space or storage than its counterpart base 10 system. For instance, 10 in base 2 system, which is 1, 0, 1, 0, requires more amount of space, which is 1, 2, 3, and 4, than its counterpart in base 10, which is 10, which requires only two amount of space, which is 1 and 2. So, the larger the base system, the fewer the digits needed for its number to be represented. Now, let's move on to converting from base 2 system to the denary or decimal system. So, in order to convert the above binary system into base 10 or denary system, the above number has a base of 2 to the power of their respective place values. That is to say, if we read from the center to the left hand side, we have 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, and 2 to the power of 3. Then if we read from the center to the decimal path, we have 2 to the power of negative 1, 2 to the power of negative 2, 2 to the power of negative 3, and 2 to the power of negative 4. 2 to the power of 3 is 2 times 2 times 2 times 2, which is 8, and 2 to the power of 2 is 2 times 2, which is 4, and 2 to the power of 1 is 2, and 2 to the power of 0, of course from the law of indices, anything to the power of 0 is 1, so 2 to the power of 0 is 1. Then 2 to the power of negative 1 is 1 over 2, 2 to the power of negative 2 is 1 over 2 times 2, which is 1 over 4. 2 to the power of negative 3 is 1 over 2 times 2 times 2, which is 1 over 8. And 2 to the power of negative 4 is 1 over 2 times 2 times 2 times 2. That is 2 into 4 places, which is 1 over 16. Now, in order to get the base 10 equivalent, we multiply each result within the value of the column and then add up the values of the subsequent result. That is, here we have 1 times 8 plus 0 times 4, don't mind my handwriting please, plus 1 times 2 plus 1 times 1 plus 1 times 1 over 2 plus 1 times 1 over 4 plus 0 times 1 over 8 plus 1 times 1 over 16 . Now, if we solve further, we get 8 plus 0 plus 2 plus 1 plus 1 over 2 plus 1 over 4 plus 0 plus 1 over 16. And then again, if we sum up this, the whole path, we will get 11. Then if we sum up the fractional path, we will get the least common multiple among these fractions is 16. So 16 divided by 2 is 8. 8 times 1 is 8 plus 16 divided by 4 is 4. 4 times 1 is 4 plus 16 divided by 16 is 1. 1 times 1 is 1. Then if we add up the fraction plus the whole number, we'll get 11 whole number, 13 over 16. So the binary number 1011.1101 has equivalent in the denary 11 whole number, 13 over 16.